Hello everyone, welcome to Study Medicine. If you liked this video, please do share and subscribe. Okay, so let's start our topic, resting membrane potential. So what is resting membrane potential? It is the voltage across a given cell membrane during the resting stage, and it happens due to the excess negative charge which create negative potential. Okay, so basically we represent resting membrane potential by writing RMP, resting membrane potential. Okay, so the resting membrane potential for nerves, it is basically -70. In case of skeletal muscles and Purkinje fibers, those are -90 millivolt. In case of SA nodes, those are nearly -55 to -65 millivolt. Okay, so first thing which there's another thing. Suppose it's a nerve cells and it is surrounded by endolymph. No, not endolymph, it is surrounded by ECF, extracellular fluid. Okay, so the potential for extracellular fluid, we consider it as 0, and then the resting membrane potential of nerves are 70. Okay, so here the trans membrane voltage difference is nearly 70. Okay, trans membrane voltage difference. Okay, now there's an exceptional endolymph. Okay, that is called as the exceptional ECF, that is called as endolymph. What is it? Is an ECF, but endolymph resembles like ICF, intracellular fluid. Why? Because of the presence of high concentration of potassium. So endolymph is an extracellular fluid which resembles as intracellular fluid due to the presence of high potassium concentration. Okay, and mostly endolymph is present in our middle ear, in cochlear region. So let's draw. Okay. Suppose this is a nerve cell and it is this fluid surrounding it, and that fluid in this particular case is endolymph. Okay, and the endocochlear potential or the potential of endolymph is being calculated as 80 millivolt, and as we know, the resting membrane potential for nerves is -70. So in this particular case, if we take the transmembrane voltage difference, transmembrane voltage difference, it will be 150 millivolt, because from -70 to +80 we calculate it as like from 170 to you have to go to 0, then to 1, then to 80. Okay, plus 80. So the difference is 70 plus 80 equal to 150 millivolt. Okay, so this is the difference in particular. So here the transmembrane voltage difference in this particular scenario is highest in our body. Okay, this is the thing which you have to keep it in mind. Now we will be talking about the ion concentration or the equilibrium potentials for an ion. Equilibrium potential for ions. Okay, during this, what is equilibrium potential? It is the potential at which the concentration gradient and the electrochemical gradient, or we can say electrical gradient, the concentration gradient and the electrical gradient will be equal. So concentration gradient will be equal to electrical gradient. Okay, now let's how do we calculate the equilibrium potential, okay, for ions? So in this particular case we use Nernst equation. Nernst equation will be used, and that Nernst equation is electromotive force will be equal to plus or minus 61 into log C1 by C2. C1 is the concentration outside the cell, C2 is concentration inside. C2, C1. Okay. Now Nernst equation is used when there is one ion is present. But what if there is more than one ion? Suppose 3 ions, more than one ion. Then at that time we use Goldman's equation. Goldman's equation. Okay. So now let's see some equilibrium potential of ions. Equilibrium potential for sodium, it is plus 61 millivolt. For potassium it is minus 94 millivolt, and for chlorine it is minus 89 millivolt. And you can see chlorine electromotive force and resting membrane potential for muscle, which is minus 90 millivolt. Both of them are somewhat similar. Okay, so during the resting phase of muscles, the movement of chlorine does not take place that much, because the equilibrium potential for chlorine is and resting membrane potential for muscle is somewhat similar. So no net movement of chlorine happens at that time.